Hello. So now we'll do this question. Let's first discuss this question. In this question, we have given a rod of mass m and length L. And this rod is hinged at the topmost point, and this rod can rotate in a vertical plane. Like if this is a hinge and this is like a rod, then it can rotate in a vertical plane. Okay. At this point, it is being hinged. So there is this small point mass here, which is moving with initial speed v. The mass of the point mass is same as the mass of the rod. So this point mass will collide with the rod. And the collision is given as perfectly inelastic collision. Coefficient of restitution there is given 0 there. So when it will collide with the rod, it sticks to it. So when this point mass will stick to the rod, obviously this rod will move upward along with the rod, along with the point mass. So we have to calculate that what should be the value of this V. What should be the minimum value of this V so that this rod should be able to reach at this point, meaning this rod should be able to become horizontal. That's what we need to calculate here. So we have to calculate the minimum speed V for this particle, which will take this rod, after the collision, take this rod to the horizontal position. Okay. So in this question, if you see, there is this conservation momentum we can apply because the collision is happening, or we can apply the conservation of angular momentum. The problem with the conservation of linear momentum is, for this system if you see, the net force is not 0. Because see, during collision, this rod will apply the impulsive force. I am calling this one for a time being, and I am calling this point as 2. So J12 will be applied by the rod onto the point mass, and similarly J21 will be applied by the point mass onto the rod. These are the action-reaction forces during collision which the rod and the point masses will apply. But during collision, this rod will try to move forward, but there is this hinge, and because of this hinge, the hinge reaction will come. And that hinge reaction will not be able to calculate right now. We don't know how much hinge reaction is coming during collision. So if you see this system means rod plus point mass. If you see this system, there are 3 forces which are acting onto this system. One is the force applied by the rod onto the point mass. Another is force applied by the point mass onto the rod. And there is this hinge reaction which is coming onto the rod. I have defined that hinge reaction as 2 components. That's what we always do, because the hinge reaction is coming at a point. And at a point, direction is, we cannot calculate direction in the beginning itself. Okay, so I have divided that hinge reaction into 2 components, Jx and Jy. One component is perpendicular to the rod, other is parallel to the rod. So you see, there are 3 forces. If I combine the system, these 2 will cancel out because they are action-reaction pairs. But this will not cancel out. So during collision, if you see, external force acting onto the whole system, I'm talking about system, is non-zero. So if the external force acting onto the whole system is non-zero, I cannot go by conserving the momentum for the whole system. So I can say the momentum of the whole system not conserved. Okay. So we cannot use this conservation principle there. Conservation of linear momentum we cannot use. But one thing we can use here, and that one thing is conservation of angular momentum. You see this point hinge, I'm calling this point O. So if axis is at point O, if you assume the axis at the point O, and if you calculate the torque acting onto the whole system about point O, if you calculate the torque acting onto the whole system, rod plus point mass, about this axis, then you see this J12 and J21, they'll give the torque which will be equal in magnitude but opposite in direction. Because you see, J12 will give the clockwise torque and J21 will give us the anti-clockwise torque. That will be equal in magnitude because the distance is same. Magnitude of the J12 and J21 is also same. So they will cancel out. And along with that, this Jx and the Jy, they are passing through the point O. Since they are passing through the point O, their movement about the point O will be 0. So total torque, net torque acting onto the whole system about point O becomes 0. So that's one point about which the net torque is 0, and because the net torque is 0 about that point, I can say angular momentum about the same point for the whole system will be conserved. So if I can conserve the angular momentum about point O for the whole system, I have the relationship L initial is equals to L final, and that too about the point O only. So first we will calculate the initial angular momentum. Initial angular momentum, if I calculate, this is equation 1 I am calling, and then one by one I will calculate both the things. If I calculate the initial angular momentum for the system, then you see this rod was at rest. So there was no angular momentum of the rod before collision. And this point mass was moving. And to calculate the angular momentum, we have a relationship, and that is linear momentum of the point mass, that is mv, multiplied with the perpendicular component from the axis onto this momentum. So this we extend the linear momentum and we put the perpendicular from point O to that extension, and that length will be the L. And the direction of this, if you see, I see the anti-clockwise direction. So that's your initial angular momentum. Then we'll calculate the final one. If I calculate the final angular momentum, you see, finally what is going to happen? Finally, this rod and this point mass, they are going to stick to each other. And the whole system is going to move with omega naught angular velocity. Okay, so this point mass will become the part of the rod. So this is a system, rigid body, it will become a rigid body system, and this rigid body will be hinged. So we know how to calculate the angular momentum for hinged rigid bodies, and that is IO omega. Omega naught I am saying because you see initial angular momentum for this rod I am assuming as omega naught. So I naught, this is the moment of inertia of the system about the O axis. Now this system consists two things, point mass and the rod. So I'll calculate the moment of inertia for the point mass about the same axis O, and that will be equals to ml square. Then I'll calculate the moment of inertia of the rod about the same point. That will be ml square by 3 multiplied with omega naught. This is 2, this is 3, and this is also anti-clockwise direction. Let's put these two values into equation 1. So from equation 1, if you see, I'll put both the values. That will be MVL is equals to, you add those two, 4 by 3 ml square omega naught. M and M cancels. So this omega naught becomes 3V upon 4L. The thing is, V is still unknown. So we get the initial angular momentum of the system after collision as a function of velocity of the point mass. Now we have to check whether this initial angular momentum for the system is sufficient to take the system to the horizontal position or not. For that, we'll be using the energy method. You see, now throughout this motion, if you see, meaning this system, complete system will be moving in a vertical circle. Now throughout this motion, is there any external agent which is acting? Yes, there are external agents which are acting, like hinge reaction you can see. But the hinge reaction, hinge reaction is not doing any work. So external agent, if you see, the work done by the external agent will be 0. Okay, you don't see any external agent, you don't see any friction. Since you don't see any friction, so the work done by friction is also 0. So we can apply the conservation of mechanical energy, and that to the modified form. So from conservation of mechanical energy, conservation of energy. So K1 plus U1 is equals to K2 plus U2. This is my state 1. This is I'm calling state 1, and this I'm calling as state 2. So state 1 is having the kinetic energy and the potential energy. So kinetic energy at the state 1, I'll write half IO omega naught square, where IO is the moment of inertia of the whole system and omega naught is the angular momentum at initial point. Now U1, this is the gravitational potential energy we are talking about, and there are 2 points, 2 systems within the single system. One is a rod and second is a point mass. So I'll calculate the gravitational potential energy for both. So if I calculate the gravitational potential energy corresponding to this point mass, you see, I'm assuming gravitational potential energy to be 0 at the hinge. So this point mass is at below the 0 level at distance L. So I'll write the minus mgl. That is the gravitational potential energy of point mass. Then again, we have to calculate the gravitational potential energy of the rod also. So the center of mass of the rod will be at this point, and which is a distance L by 2. So I'll again take the minus there. So minus of mg L by 2. So that becomes the gravitational potential energy of the system at state 1. Now that is equals to the final kinetic energy. Now let's first write the potential energy, final potential energy. Now you see, if you see the finally, the center of mass of the rod comes to this level, as well as the point mass also comes to this level. So both the points come to the same level, and the level is 0 level. So gravitational potential energy for the whole system finally will become 0 plus. And since we want to calculate, let's say the system is having some kinetic energy at the state 2. I'm writing that kinetic energy K. Okay, so you see this value half IO, you can write the system's moment of inertia, we have already calculated here, half multiplied with 4 by 3 ml square omega naught square is equals to, I'll take that on the other side, 3 by 2 mgl plus K. Now see, as this omega naught will tend towards minimum, this K will also tend towards minimum, and that minimum is 0. So when this kinetic energy, final kinetic energy will become 0, we will get the minimum possible value of omega. And corresponding to the minimum possible value of omega, you see here, this. Corresponding to the minimum possible value of omega, we will get the minimum possible value of V, which is the question. In the question, we have to calculate what will be the minimum value of V. So when the V will be minimum, omega will be minimum, and when the omega will be minimum, final kinetic energy will also be minimum. So what we will do in this equation, we'll put K as 0. And when the K will become 0, omega will also become minimum, not 0, but minimum. So this value, 2 by 3, this 2 and 2 cancel out. ml square. This omega, you see, this in place of this omega, I can replace this value. 3 V minimum upon 4L whole square. And that is equals to 3 by 2 mgl. So m and L here, m and L. Okay, take that. This. So it will be equals to, we'll square this whole value, 9 V minimum square divided by 16 L square, and that is equals to, it will take it here, 9 upon, this 2 will take there, 4 G. Okay, this 9 and 9 gets cancelled out, this 4 cancel that 4 times, and you see there is this L which will cancel this L. L we were taking here, so 1 L will cancel this one. So this V minimum becomes 2G L. This L will go there. V minimum square. And that will make V minimum to be equals to under root 2GL. You see, if the point mass will be having this minimum velocity, if the point mass which is going to collide with the rod, if that point mass will be having this much velocity, then after the collision, the whole system will reach to the horizontal, minimum at the horizontal, and there the system's velocity will become 0. System's angular velocity will become 0. So that's the minimum velocity required. That's the minimum velocity required for the point mass to bring this whole system to the horizontal position after the collision. Okay. So that's how we solve the equation. If you see, in the beginning we were checking with what kind of equation we can use, whether we can use the linear momentum equation or we have to go for something else. So we realized that linear momentum equation we cannot use because of obvious reasons. These are the reasons. Then what we did, we went with conservation of angular momentum by taking the axis here, which made the torque acting onto the system 0. If I take axis at any other point, torque will not be 0, and the momentum, angular momentum will not be conserved. So that's only for this point. Okay. Then using that concept, using that trick, that axis, we calculated the angular momentum and we equated that. And from there we get the relationship before and after collision. And then we extended the problem using the work energy theorem, and we calculated the minimum velocity required for the system to become horizontal. Okay, that's how we solve the question, this kind of question. We'll solve some more questions later on. Thank you.